The most remarkable theorem. Part 1. Curved space. Germany. Around 1787. A young Carl Friedrich Gauss sits in his grade school classroom and ponders the solution to an arithmetic problem on the board. Add all the counting numbers from 1 to 100 together. That should surely keep the students busy. While others around him would scratch away calculations on their slate boards, Gauss began to visualize his solution, a pattern amongst the problem. Within minutes, he had a solution. The answer came to him. He imagines adding the same list of numbers to itself backwards. This in turn produces 100 copies of the number 101. So, 10,100. But since this is double the value that we actually needed, dividing this number by 2 gave him the solution. In minutes, 10-year-old Gauss returns the answer to his teacher of 50/50. This would be the beginning of Gauss's demonstration of his genius. Amongst the many things that he did throughout his life, he proved the constructibility of the regular 17-gon, something that had eluded the ancient mathematicians for hundreds of years. And among his other achievements, Gauss is responsible for the fundamental theorem of algebra, which connects the degree of a polynomial equation to the number of solutions that it can have. And although this result would be enough to solidify Gauss's name in the mathematics history, this would pale in comparison to what he would develop while working as a surveyor. To measure the Earth, he invented the heliotrope in order to make accurate measurements of distances. And during this time as a surveyor, he would develop concepts of the least squares approach to finding the line of best fit. Later, he would develop areas of statistical analysis by exploring normal or Gaussian bell curve distributions. Perhaps, though, it was the difficulties of measuring surveyed curved surfaces that led him to the discovery of what he would call in Latin the Theorema Egregium, or the remarkable theorem, a theorem that would blossom into the study of differential geometry. Now, in order to make a map, one must measure angles, distances, and areas accurately. So what is the problem with making a good map? Well, for one, maps are typically flat, and the world is not. It's curved. And so are the paths traveled around it. So just how do you flatten a sphere? Many attempts at making maps flat brought to light a simple problem. When you flatten a map, something gets distorted. Here is the well-known Mercator map. And what is good about it is that it preserves angles. But areas become distorted when you move closer to the poles. Now, other maps have been put forward, for instance, one called the Gauss-Peters map, which preserves areas, but angles get distorted instead. And so that changes the point of view from someone navigating with such a map. In fact, here's a picture of the Gauss-Peters map. So although it accurately depicts the size of land masses, going in certain directions would be difficult because angles are not preserved. And so we are now led to the conclusion that we must get a better understanding about how curved surfaces work by examining curved paths, known as parametric curves. Coordinates of a point along a curve can be described by a set of functions parametrized by a variable t called the parameter. As t increases on some interval, x and y as functions of t trace out some curve. And to get a unique perspective on this matter, we will have to see the world for a bit from the viewpoint of an ant. This is Anthony. Imagine an ant circling a picnic blanket. A unit circular path can be described by the parametric equations x of t equals cosine t, y of t equals sine of t on the interval for t from 0 to 2 pi. So although t is like time ticking away, we can also view it as an angle that the radius passes through while it rotates about a center. And sometimes this set of equations are called polar coordinates. This is motivated by the connection between right triangles, circles, and the Pythagorean theorem. So on a flat picnic blanket, Anthony can choose many different paths to get to a sandwich. However, he knows from his days at Anthill High School that his shortest distance between him and his lunch is a straight line. And so Pythagoras shows us that the length of such a line is given by the square root of a squared plus b squared, where we imagine this right triangle setup and the diagonal is the straight path for Anthony to travel. But here's the thing, Anthony's cousin Felix happened to climb a helix to get to some high-end snackery. And wouldn't you know it, Anthony wants in. So let's explore Felix's helical path, which is a curved path. And so it raises the question here, just how do you find the length of a curved path? The answer to that starts with vectors, mathematical objects that have both length and direction, and we represent this by an arrow. Vector notation shows that the length of any vector is given by the sum of the square of its components under the square root. In other words, the Pythagorean theorem is put to use here to find the length of a straight vector. Now imagine along some curve in space we draw some tiny arrows along each tick of time and use them to measure the lengths, and these are vector curves. So the vectors along this curve are called tangent vectors, and so we might think about taking a curve given by x of t, and on some interval from a to b it curves out some path. And if we were to divide this curve up into some sub-intervals and draw line segments connecting each endpoint of these sub-intervals respectively, we could then estimate the length of this curve by adding up the lengths of all these line segments. So if we approximate the length of the curve by adding up the line segments, each line segment will have a length that we will call delta S. And we will sum these lengths up to get the total length of the curve. Now, because these are line segments, we're just finding the distance between 2 points on a line segment. So delta S can be found by doing the Pythagorean theorem, or the distance formula in 3 dimensions here. And so as the limit as time delta t goes to 0, this defines something of an integral, a definite integral, on the path from a to b. And because our line segments are really tangent vector arrows, it is their lengths that we are summing up along the integration path. So the arc length of a curve over some interval by given parameter t here is this integral from a to b of the length of the tangent vector integrated over the path. So if this is the integral formula that we need to use to calculate arc length, let's do a sanity check here by going to something familiar. Recall that a circle of radius a has a circumference, or an arc length measure around its edge, of c equals 2 pi times its radius, so 2 pi times a here. So our formula for this circle should match our arc length calculation. And with a radius of a, our circle parametrization in R2 is given here. To calculate the arc length using the integral from 0 to 2 pi, we will need the tangent vector calculation, and so we differentiate each of the functions inside the vector. And then calculating the length of that vector, we take the square root of the squared components added together. And then we will integrate that value, which here, that length happens to be a constant, and we'll integrate that from 0 to 2 pi, giving us 2 pi times a. So, check. It gives us exactly the circumference of the circle, or the arc length around the curve. Okay, so now it's time to return back to Felix's helix in 3 dimensions. The parametric equations here should emphasize why a helix is a rising circle, or better, a spring curve. Following the same procedure as our circle, the length of the tangent vector is constructed, and we find that to be the square root of a squared plus b squared. And so the arc length will be calculated by the integral from 0 to 2 pi here, of that particular length integrated, and we get 2 pi times the square root of a squared plus b squared. And we can make a quick comparison to this value and the straight path that Anthony took on the flat plane. So one can also expect that a helical path is greater than a circular path of the same radius, and we can show that here by this inequality. So one natural question that does arise is to ask the question, is there in fact a best way to parametrize a curve? Is there one parameterization that is better than the other? So to consider this, let's think about a parameterization of a line in R3. And we're going to give 3 different parameterizations of the same line, given by x of t, y of s, and z of u. Now if I animate this, we can see particularly, let's start with a point on x of t. We'll call that point A, and I'll animate that here in pink. As we look at the way that A will move along the curve as we let the parameter trace out the curve, okay, we'll see that if we let it go through its entire range and its parameter, it will trace out a straight line. So let's illustrate that straight line here in 3 dimensions. Okay, so it's a linear path, and we can show by graphing the 3 different parameterizations. Here we'll graph y of s, and I'll have a particle, we'll call it b, moving along that path. And we can see it's the same linear path as x of t. But one thing that we'll notice about these different parameterizations, and here I'll illustrate the third one moving along the same path, is that each particle, quote unquote, will move along the path at some different rate of speed. In fact, the speed will be variable along the curve depending on the choice of parameterization. Alright, so what we would want to know is if these particles can move in a best way. In other words, is there a best parameterization to use? The answer to that is in fact yes. There is a best way to parameterize a curve, and picking a best parameterization starts with a goal. The goal would be a particle moving at unit speed, a speed of length 1. Parameterization by what we'd say arc length, let's call that s, would give us such a unit speed. Let's unpack that idea a little bit. So by parameterizing a curve by its arc length, we'll use again the variable s for the arc length, a particle moving along this curve will move at unit speed, which is the length of the velocity or the tangent vector along the curve. So that means that the tangent vector will have a length of 1. Now if we define a function, an arc length function of time t, it would be given by the same integral that we defined earlier, over some path from a to a variable t. And so differentiating s would be differentiating this particular integral, and we're just using a dummy variable of tau here for integration. That would help us define the speed function of our path. Now, arc length parametrization here, given by this integral definition of the integral of the length of the tangent vectors, okay, a re-parameterization is possible for the particular helix. So what we want to do is we want to take S and solve it as a function of t, so that we can replace t in our parametric equations with something in terms of S. So here's our helical path, and we'll choose the point P0 to be our starting point along the path, and that would be if at time equals 0, and we'll get that vector A00. So the path from 0 to time t will allow us to give us a function of time, and this is not always easy to calculate, this type of integral. Since the tangent vector length is a squared plus b squared under the square root, we're going to integrate that from the integral from a to t. And we can let a here be equal to 0. So the integral comes out to be the square root of a squared plus b squared times t. So s can be written and expressed in terms of t, and therefore t can be, in turn, expressed in terms of s. This is our re-parameterization of our curve so that things move at unit speed along the curve. And so just replacing t with s over the square root of a squared plus b squared, we get our re-parameterization. And if I took the tangent vector length here, it would have a length of 1 all the way along the curve. So this is our helical path parametrized by arc length. Now we can make a few observations here. The tangent vector can be rewritten in terms of x prime of s times ds dt according to the chain rule. And ds dt is the length, the magnitude of the tangent vector there in terms of t as a function. And so we can write x prime of s as the tangent vector divided by its length, which is another way to say that we have normalized a tangent vector to make it a unit tangent vector, which simply means a tangent vector of length 1. Okay, so a re-parametrized curve will have tangent vectors of unit speed, which does not depend on the speed of the original parametrization. Alright. Now, since S is often hard to compute, we often will want a particular parametrization that makes the arc length computable. But here, let's just demonstrate what I mean by this. Consider two parametrized paths that are very similar to each other. X of t and y of t. Now you can see their similarities, but when we calculate s for the first curve, we get t plus t cubed over 3, something straightforward. But for y of t, that integral has no closed form formula solution, and so therefore it is hard to re-parametrize the curve according to that. So we now ask the question, why are unit tangent vectors so useful? In the study of curves, unit vectors can help us define something called curvature. And curvature is simply how much a path bends away from a straight line path. Now consider a path with a non-zero speed. And when we consider a curve with non-zero speed, we do so that we can normalize the tangent vector. Another way of saying that is that we can not divide by 0. Okay, so throughout this we'll assume that our tangent vector has non-zero speed. Okay, so if we take this path x of t, and we require that it has non-zero speed, we can make a couple of observations that will help us define curvature. 1. The derivative of the unit tangent vector will be perpendicular to the unit tangent vector. Since both of these will be vectors, they will be perpendicular to each other. And the length of the derivative of the unit tangent vector is measuring the angular rate of change as t increases of that unit tangent vector. Essentially, as you move along the curve, the unit tangent vector will turn. And so we define curvature as the length of the derivative of the unit tangent vector divided by ds dt. Or another way to say this, it's the length of dt ds. Now what we'll learn later on that this is an intrinsic property of the curve and does not depend on the parameterization, or I should say, the coordinate system in which we are using. A better way to visualize this is imagine two vectors perpendicular to each other. I'm going to neglect orientation here for a moment. Overlapping these two pictures, we see that the angle change, theta, between the two tangent vectors here is a measurement that is directly proportional to what we would call the curvature of the curve. So again, capital T dt is measuring the rate of change of theta as t increases over the curve. So essentially, it measures how much the tangent vector will turn as it moves along the curve. And if the curve is re-parametrized by arc length, the curvature is just the magnitude of dt ds. Okay, let's get a better handle on what curvature is talking about as a numerical value. Okay, imagine a path that is close to being flat, that is not very curved. If I draw the tangent vectors along this curve, we can see that they don't turn or twist very much. So very little twisting of the tangent vectors translates to small curvature. So little or small tangential rotation is the flat of the curve. Now, if we have something that's really curved, like let's say a spiral curve, we get a lot of turning on the tangent vectors. And so this indicates a large degree of curvature. This is something that translates later into something called tensors and Riemann curvature. So here, just the curve of a spiral is much more twisty than another curve that is flatter. So let's go back to another sanity check and come back to this circle of radius a, which we know has an arc length of 2 pi a. Setting up the formula for curvature, we can calculate this by going through the fact that we know that ds dt from an earlier calculation was the length of the tangent vector a, which is also the length of the radius here. And so that would give us the unit tangent vector here of negative sine of t cosine t. So when we calculate the curvature, we get 1 over the radius a constant amount of turning around the circle. And it would make sense that if a gets larger, the radius of the circle gets larger, the curvature gets or seems flatter. Like people living on a giant sphere believing it to be flat. Another sort of sanity check here would be to check that a line gives us a curvature of 0. It is the essential idea of being flat. So we can parameterize a line in space by two constant vectors a and b, and we have at plus b. The derivative of x of t would just be the vector a, the constant vector, and that has a length, which is a constant length, given by the formula for the length of a vector. So the unit tangent vector is the length of the vector a divided by its length. And since the derivative of a constant would be 0, we're showing that the curvature, by definition, would also be 0. So check, a line never curves. So now let's go back to the helical path. And we have here in 3 dimensions, the rising circle. And now, if we encountered some curvature by climbing this curve, what kind of curvature would we calculate? So going through here, first getting the unit tangent vector. Then of course we want to differentiate that with respect to time to help us define the curvature. And recall that the curvature is the length of the derivative of the unit tangent vector divided by ds dt. And we knew that ds dt here was the square root of a squared plus b squared. Okay, so putting this all together, we find that the curvature for our helical curve is a over a squared plus b squared. Another constant. And if we let the limit of b go to 0, in other words, we slice a plane in this spring, this degenerates down to the circle with a curvature of 1 over a. Okay, let's review. The key concepts. In Euclidean geometry, or flat planar geometry, the Pythagorean theorem gives us a distance formula. But in 2 or 3-dimensional space, parametrized curves are the way that we describe curved space or curved paths through space. Vectors and their lengths are defined here as follows. And when we need to calculate the arc length of a particular curve, we're going to use the length of the tangent vector to do that. And essentially that's taking the length of these line segments along the curve and calculating them through a continuous limit, giving us the integral. And the length of the tangent vector is what we're integrating along this curve. Re-parametrizing a curve by its arc length s gives us a particle moving along this curve at unit speed. And that means that the velocity or tangent vector has a length of 1. We can re-parametrize a curve by its arc length, and we can define the re-parametrized curve and the derivative of that as the unit tangent vector. We call that t, the normalized tangent vector. The derivative of that vector and that vector itself are perpendicular, and we can use that perpendicular set of vectors to measure something called curvature, orientation not being considered here. And curvature measures how much a curve bends away from a straight line, and it is a numerical quantity but can be calculated as a function along the curve. And as we did some checks here with the circle, the straight line, and the helix, we saw examples of constant positive curvature or zero curvature. Given a path, x of t, can you find the arc length parametrization of this curve and calculate its curvature? In part 2, we'll talk about torsion, the moving frame, and surfaces. For now, thanks for watching. Please hit that like, subscribe, and notification bell for more videos, and stay tuned for part 2.